Okay, so this video is going to be a quiz, not quiz. I don't think I've ever actually mentioned why quiz, not quiz is called quiz, not quiz, so we'll talk about it now. Um, Maybe I have. Who knows? The whole point of a quiz, not quiz is to treat it like a quiz. Treat it like your grade depends upon it. Um, that causes you to focus. It causes you to use more engaged learning types of ways of interacting with the problem. So, and this all comes from noting that when I used to give in-class group quizzes for grades, people learned a tremendous amount from them, but it was unfair with the grades how to apportion the credit. So I stopped making them for credit, but I still wanted to have people focus like they were for credit. So I started calling them quiz, not quiz. So with this quiz, not quiz, and just a reminder, skip this video if you're planning on going to class, because we'll do this in class, in groups and breakout sessions. But if you're not going to be able to make it to class, then feel free to work on this on your own a lot. Work on it with other people. The whole point is to discuss it with other people, and then come back to the video and perhaps discuss the video with people. Cool. So we want to draw streamlines. So that so airplanes use the following arrangement to measure airspeed. There is a tube that it comes out of the plane and points forward. The air coming relative to the tubes is coming in this direction like this. And you've seen one of these on a plane if you've ever walking on the, I forget what it's called, but you can see them sticking out of a plane. And then next to this tube, there's a small hole that is connected to that tube via a differential pressure sensor right here. So this will measure the difference in pressure between this point and this point right here. Cool. So we're going to draw the streamlines starting from the given points here. These given points, and then we want to look and see if there's a stagnation point. And will the bottom tap disturb the flow if it's small? So I'm going to draw this streamline. It's going to go over the top. Not going to do anything. This one's going to come. It's going to hit this right in the middle, and it's going to stop because this is all plugged up, right? Flow can't go in this direction through this thing, so it's effectively a dead end. And this one's going to come around. Going to come around this. This is going to come around that too. Around, and then this one's going to come, and it, as long as we make this hole quite small, it's actually not going to disturb the flow that much. Great. So we've drawn that, and we've drawn a small hole in the surface, and I've drawn this actually how they make these holes in real life, because they found that it disturbs the flow even less if you create a small little settling chamber outside of the hole. So right inside the hole, I mean. So the hole widens up, and then it narrows again to another tube before it gets to the differential pressure sensor. And then the question is, how would we use this to measure airspeed? Well, I'm going to draw an imaginary streamline from here, right next to this flow, where it's stagnant but touching that flow. So it's stagnant in here because this is a dead end. We're going to cross that, pretending like we can. Then we're going to go up to here, and I'm going to end here, right in touching that other streamline, which comes to an end. So all this fluid inside of here is stagnant, which means that right. Sorry, it's so all the fluid in here is stagnant. So what we're going to do now is we're going to write Bernoulli's for this equation. So we're going to say that 1 P1 plus rho V1 squared over 2 plus GZ times rho is equal to, that's Z1, is equal to P2 rho V2 squared over 2 plus G rho G Z2. Awesome. So we're going to have to assume some things. So let's assume gauge just to make our lives easier. So gauge pressure means P1 and P2 We don't know quite what those are, but we're not too worried about it right now. Z1 and Z2, we aren't given any heights, but this is air, right? It's a gas. So we're going to assume neglect mass of gas. That'll be B, A. So if we can neglect the mass of the gas, height doesn't matter. Potential energy doesn't matter. So we can make that 0 due to B. Awesome. We know that the velocity of the streamline that we're touching, let's do that one. The velocity of the streamline that we're touching here is 0, so the V, we didn't label these. Let's label this 2 and 1. We know that V1 is approximately equal to 0 because that's a stagnation point, right? So that's 0. Great. And so our differential pressure sensor will tell us the difference in pressure between point 1 and point 2, and we want to know the velocity of the streamline that is directly adjacent to this tap where we are measuring it. And so if we solve for V2, we find out that 1 to 2, V2 is equal to the square root of 2 times P1 minus P2 over rho. So if we wanted to use this as a way of measuring, and remember P1, P2, difference between P1 and P2 is exactly what this differential pressure sensor is going to give us. If we know the density of the air, which we can usually get from a temperature and height table, or by, if we know the absolute pressure outside, we can get it from ideal gas law. Then if we know the density and we know the difference in pressures, we can solve for the velocity that our plane is going relative to the air. And this is a really important object on a plane. And it's a really important object because, especially for airliners, they're often surprisingly close to stall speeds. Closer than you would be comfortable with if you knew it. And so in order to know whether for the pilot to know or the autopilot to know if they need to change their speed in order to prevent stalling, they have to know their speed relative to the air. And it's not uncommon. These are often heated to prevent this, but it's not common, but it has happened where these tubes have frozen over, and if they freeze over, like let's say this one freezes over here, or this one freezes over here, it's no longer in contact with this air, right? So the pressure it reads is no longer related to the velocity of the pressure right directly adjacent to it, or directly adjacent to it. So as a result, you get this delta P is not related to the speed, is no longer related to the velocity of the air outside, and so the velocity that your sensor is calculating is erroneous. There are ways of checking this, but yeah, it's not easy. Cool. Bonus question: is this a valid streamline? And the answer is no, right? Because we crossed this differential pressure sensor. But it turns out it really works, right? And one of the things we talked about with Bernoulli's is Bernoulli's really works surprisingly well, even though you have to break a lot of its rules in order to use it oftentimes. And remember, one of the assumptions we're using here is that our streamline starts and ends so close to these other streamlines that there's no pressure gradient, significant pressure gradient between the two. So imagine that we're starting. Let's erase this again. This is point 2. Imagine that we're starting it right here. This is basically stagnant fluid, and it's directly really close to this fluid right here, which is moving at a high speed. It's not physically realistic for there to be a large pressure gradient between these two things. So the pressure at this point, and hence the pressure throughout this entire tube, is going to be related to the pressure of the fluid right there. If it weren't, let's say this pressure is lower in this streamline because it's moving, what's going to happen is the high pressure in this tube is going to cause the air to leave. So as a plane speeds up, this tube will actually drain of some of its air because of the lower pressure outside of it due to the moving fluid, until the pressure is inside of this tube is equal with the pressure of this streamline right next to the surface. The same is true of this tube. Initially, as the plane is speeding up, the stagnation pressure here increases and increases and increases. Remember, the stagnation pressure is equal to the P surrounding plus the 1/2 rho v squared over 2, the kinetic energy of the fluid. So all this kinetic energy is being converted as the air slows down into pressure here. And if the pressure here is not the same in the tube is not the same as right here at the entrance of the tube, then fluid will flow in this direction until the pressure is equal, which basically means that the density of the air increases in here and the pressure increases until the pressure in this entire tube is equal to the pressure out here. Now, there can definitely be a lag if this tube is very large between the pressure out here and the pressure within the measured by the differential pressure sensor, but usually these tubes are very short to prevent that. So, great. Hope you guys had fun. Practicing this problem. Don't forget that I got carried away. We have to assume inviscid flow and steady state in order to use this equation well. And again, inviscid flow, it's probably okay here in this particular case because we don't have a lot of flow through small tubes or anything like that. And steady is a decent assumption here too. Great. Next time we do a video, it's going to be on this practice problem, flow over a wing, and flow measurement in pipes.